So now to have a little more in-depth understanding of this, take a numerical. Take Ke is equal to 100, P is equal to 1 Newton, 100 Newton per mm, and Kp as per this analogy, it becomes 10 power 4 times the K. Solve for U1 now. P by Kp. What is U1? P by Kp. What do you get? P by Kp. U1. 1 into 10 power minus 6. What is U2? 1 plus Kp by P by Kp. What is P by Kp? P by Ke. P by Ke is 1 into 10 power minus 2 plus 1 into 10 power minus 6. What is the variance here? 10 power minus 6. And what is the dimension we are getting? 10 power minus 2 is the actual value. If you look at this here, 0.01 mm is the value we get. 0.01 mm is the actual value. Because of this representation of penalty, we will be getting 3 additional zeros and 1. This is the variation. For U1, in place of 0, we will be getting 0, 0. So our 0, actually, this is the error we are getting in U1. In place of 0, we are getting this. In place of 0.01, we are getting. And this is even comparable to the truncation errors, much less than the truncation errors what we encounter in our computations. So that's the reason why this penalty approach is widely used. So whenever we have a support, this will represent this as a given penalty, and this penalty is coming in the direction of U1. In other words, if you recall the equilibrium, what you get here, Kp into U1 is the additional force we are getting, additional resistance we are getting. The support is offering a reaction in this direction of magnitude Kp times U1. Support has a huge stiffness, and that will offer resistance exactly in the opposing direction. The additional resistance it is going to encounter due to the support that we are representing in the penalty. That's why it's a lump of mass, a penalty force we are introducing in the direction, in opposite to the direction of U1. And later we see what happens if there are multiple constraints. Constraint having more than one displacement, how to tackle, that is going to build up based on this philosophy. Once this is clear, then we will clearly get the idea how to introduce various other constraint equations, including the contact problems. That we'll see in due course of time. It is clear now to this? So now we'll move to the next part. How to consider the same problem with more than one element. Two elements or three elements, four elements, when we need to go for more number of elements, what to do? What is the basis for this? Any idea now? We'll try this with two elements first. Is the concept of penalty clear? Any doubts on this so far? Any doubt on the topics notes so far? Now the same problem we are going to tackle, but this time two elements. So how to use the connectivity? How to put the set of equations together? This process we call assembly. The major concept we are going to understand here is assembly. Assembling the element stiffness matrices to get the system stiffness matrix. The system stiffness matrix at times is referred to the global stiffness matrix. That's a very popular name. First we establish the stiffness matrices for the elements, then we put them together, then we get system or global stiffness matrix. So let us start with the same problem. This is our problem. This time we try to make this into two units. Let us say this is L by 2, this is L by 2. Problem being the same dimensions. Here we have the load P, E is the length modulus and A is the area. And now let us consider this into two elements. Let us say this is element number 1. Say another element. This is element number 2. This is node 1 for this element. This is node 2 for this element. And this is node 1 for this element. And this is node 2 for this element. Now what are the displacements here? This is U1. This is also U1. This is also U2. Now there is a conflict. As far as node numbers are concerned, we are not going to use them further. But when I say U1, U2 here and U1, U2, then there is an ambiguity. So let us distinguish them by giving one more superscript, giving the element number. This is element number. Now we add element number. So U1, U2 earlier, because one element, we are not bothered to give another tag. Now we are giving another tag, a superscript, which indicates the element number. Now let us see element number 1. What is stiffness equation? What are stiffness equations? L is equal to length of the element is equal to L by 2. So for this, Ke for element 1 is equal to Ke for the element 1 is equal to, what is it here? Ea by L 2Ea, because L length of the element being half of the original length, so this is 2Ea by L. What are the stiffness equations we get here? 2 Ea by L 1 minus 1 minus 1 1 U1 of 1 U2 of 1, right, is equal to, from the stiffness side we get this. Clear? And for the, in the physical sense, if you take a bar, what does it represent? What does it represent? In this direction, we have, if you call this, we are representing this as Ke of 1, right? Shall we say this is Ke of 1 times U2 minus U1 in opposite direction? The direction is reversed, so we say Ke times U2 minus U1. No, sorry, U1 minus U2. Here we have, what do we have here? Ke1 times U2 minus 1. So this is what we get. That means the moment we represent this in this form, just the internal, whatever we get from the stiffness, this is going to represent the internal resistance offered by the body towards the external loads. The stiffness side, we are representing just the internal resistances data. So here, when I am looking at the influence of this entire elastic body at these two nodes, this can offer this kind of resistance here and this kind of resistance at this. Of course, both are equal and opposite, but to represent them in opposite to the opposing, we take reactions opposing the external positives. So we represent this in this fashion. So these are the resistances that are developed. Okay, and this is in terms of, if you take U1 of 1, U2 of 1, U2 of 1, and 2. And if you take the element number 2, again KE of 2 also will be 2EA by L. That will be KE of 2, 1 minus 1 minus 1, multiplied with U1 of 2 and U2 of 2. If you represent this in a symbolic manner, we say KE of 2 times U1 of 2 minus, and here we get this as KE of 2 times U2 of 2 minus 1. Right? So, when we say when the entire number is modeled as a single element, the entire resistance is lumped at these 2 points. What was the resistance at that time? EA by L into E1 minus E2. Now, at the moment we make this into 2 elements, the resistances are lumped at 3 locations. Right? Now, how many discrete equations are going to get? 3 discrete equations. Earlier, we are assuming the entire body continuum equilibrium is represented as 2 equilibrium equations. The moment we make them into 2 elements, there are going to be 3 locations where we establish the equilibrium. By the way, if you extend it to 3 elements, what happens? Extending the number of equations of equilibrium. If there is a need, we can go to the number of equilibrium equations as many as you wish. In a continuum form, they are infinitive. When you convert this to FEA approximation, there are finite in number, and that number is based on our choice. We have a freedom to choose that number. Is it clear? Now, let us write the equation for this. I am writing for the convenience, I am writing like this. KE of 1 times U1 minus KE of 1 times U2 is equal to the resistance what we get here. And at this location we have KE of 1 minus KE of 1 into U1, I rearrange them, plus KE of 1 times U2. Both are equal and opposite. For the convenience, I am rearranging. Okay? Then this is the resistance offered by the first piece at this end. This is the resistance offered by the first piece at this end. Same way, look at this element now. KE of 2 times U1 of, this is U1 of 1, U2 of 1, U1. They are all corresponding element 1. And this for 2 minus KE of 2 times U2 of 2 is equal to, and so this is the resistance at this point. This will be KE for 2 times U1 of 2, but is opposite, plus KE of 2, U2 of 2 is equal to. So now these are the resistance. Now what we have done, this is the structure. We have divided it into 2 pieces. We made that into 2 pieces, and we established the equilibrium equations for these 2 pieces separately. Right? So the element, we call them as elemental equilibrium equations, or element constitutive equations. The stiffness we call constitutive. So these are the element characteristic equations, not constitutive. Constitutive is different. So these are element characteristic equations. Now we have 2 equations for element 1 and 2 equations for element 2. Right? Now we have formulated the equations by dividing the domain or dividing the structure into two pieces. We would like to get back the equilibrium equation for the structure. What is the logical step? Physically, by putting the two pieces together, we get back the structure. So take this piece and put them together, we get the same structure back. Right? Now independently, each element has two ends, two nodes. We got two equilibrium equations. These two ends are in equilibrium for this element, and these two ends are in equilibrium for this element. When we put them back into the structure, now what is the condition? When you assemble them back, here this is a common junction for both elements. So this point belongs to element 1 and this point belongs to element 2, and physically both are one and the same. When I put them here, now let us see, here we will be getting this from element 1. Element 1 is offering some reaction here. This we say E1. Resistance of element 1 RE1, RE at 1, let us say. Resistance at 1 for element 1. This entire thing we can write. So this is the resistance at end 1 of element 1. And this is the resistance at end 2 of element 1. When I put back this element, and its equilibrium equation is also when we bring back, so this is the reaction from element, resistance from the element 1, and this is the resisting force from element 1 at this end. Now let us pick this element and position here. What are the resistances it is bringing in? This also brings something along with this. What it gets? This is the resistance offered by this piece at this location RE1 of 2. This is bringing in resistance here RE2 of 2. Right? Now when this entire structure is in equilibrium, this physically in same location. So what is the net resistance offered here? Contribution from this piece and contribution from this piece are, both these elements are contributing at this location. We have a contribution from this region and from this region. The net contribution is sum of these two. That's one thing. And we are going to add up these contributions. How many variables are there here? U1 only once. This U2 of 1 and U1 of 2, can they be independent? Can they be different? Can they be different? Whether at once we are referring, when we are thinking of this point that belongs to this side, we designate this as U2 of 1 for convenience. Same physical location, when dealt with this element, we have designated this as U1 of 2. But they are not distinct. They are not different. Both are one and the same. For formulating the equations at the element level, for the convenience, we have used the local notation. But now, can we bring in a notation which is common for all? So we are going to bring in the global variables now. For that purpose, what we see here, we can write here itself, U1 of 1 and U2 of 1 and U1 of 2, both are one and the same, they cannot be separate. Then we say U2 of 2. In the local sense, we have 4 variables. In global sense, both being same, we can designate as a single variable, total element only 3. So let us give a name, say U1, U2, this is global. Local we are using lowercase u and global is for capitals. Now we can replace this with U1, this with U2, this with U1, this with U2, this is our U2, this is U3, this is U2. We can rewrite these equations just by introducing the global variables in place of local variables. We can rewrite these equations. Now, when we assemble the elements physically, we get a structure. By assembling these equilibrium equations, we get the equations of equilibrium for the structure. Where they are going to be joined in this case? At node 1, this is as it is going to come. At node 2, in the direction of U1, there is only one contribution, that will be KE1 times U1 minus KE1 times U2. And coming to the second part, at the node 2, there are two contributions. This is a contribution from element 1, this is from element 2. So here, this is in the direction of U2, we have KE1 of U1 plus this U2, we have two coefficients. This must be added to this physically. By adding these two, we are getting the total resistance at that node. So this we can say KE of 1 plus KE of 2 times U2 minus KE2 times U3. Then we have last equation is only one, so minus KE2 times U2 plus KE times U3 is equal. Now if you say this here, by assembling the stiffness contributions, just we get the portion of the equilibrium equations, and they literally represent the lumped resistances offered by the structure at chosen discrete locations. How many in number? How many such equations we get here for the structure? These three are the global degrees of freedom for the structure, or simply the degrees of freedom for the structure. In local sense, we have only 2 for each element. There are 4. By introducing the compatibility, these two cannot be continued. By continuity requirement, these two cannot be different. So to have a continuity across the element boundaries, we impose a condition, these two are same. So both are represented the same variable. We will be getting reduced number of variables. At the elemental level, we will have more degrees of freedom. By using this continuity requirements, we will get a reduced number of degrees of freedom, or reduced number of discrete variables. At the element level, there are 4 discrete variables. In a global level, there are only 3. 2 of them are same that we have introduced. Once you have this, what next? What do we get here? Now, if we see the direction of U1, in a physical sense, we have a support. This support we have to bring in. That support we can define in terms of a unknown boundary reaction. The moment we clamp it, the clamping is going to bring in support reaction. Unknown support reaction it is going to bring in. Then at the other end we have a load P. Now can we bring this P directly to the system without much trouble? What is the work done by this load P? If I look at now at this stage, I keep this load vector, this point load aside so far, we have not even bothered. Now we would like to bring it. What is the contribution of this load P? P into the displacement at that location. P into U3. Where does it appear? Now there are two ways I will explain. One is P into U3 is the additional term in work potential. When we differentiate with respect to U1, we get first row. Differentiating with respect to U2, we get the second row. With U3, we get the third row. P U3, where does it appear? In the third row. Minus P in the left hand side, or P to the right hand side. That is one. Or when we bring in, the influence of this P is of assembly or before assembly. Here we have a load P. All these forces are representing on the left hand side, so this will be obviously on the right hand side. We get P. That is the point load P. Now we can put them into the equation form, in a matrix form. Put the value of Ke and you try to solve for the displacements. take the numerical values 100 for KE, AE by L is equal to 100, P is equal to 1. Maybe you can try to solve this equation using elimination as well as penalty approach. And you can try. For second equation? There is nothing. See, they are together. Is any external force is there? Any boundary is there? Any additional condition is there? Then nothing is there. It is simply 0. If you use a penalty in the direction of U1, so the penalty stiffness will add to this stiffness. If it is elimination, this entire row will be eliminated. This entire column corresponding to U1 will be eliminated. We will be having 2 by 2 equations. Both ways we can try. So before the next class, because we are going to have a little longer time, as I told, Tuesday class will not be there. So you have enough time. First you solve this same problem, you solve it with 2 elements, then do it with 3 elements. Any difficulty if I ask you to extend with 3 elements? You do it. With just, you spend 10-15 minutes, you do it. You get yourself comfortable in assembling these equations. Later I will tell you another approach of assembling the equations to be a slightly different approach. That's for ease of assembly. Later even I will give you an algorithm to do it in a code. So for today we conclude this here. Any doubt on this? So when we formulate the equations of force at element level, literally we are bringing in the equilibrium for the element at the chosen nodal locations. The equilibrium of the entire element is represented in terms of 2 discrete equilibrium equations, say lumped. We are lumping the entire resistance of the body at 2 locations. In vibrations we call it the lumping. So here you say it is discrete with finite number of degrees of freedom. But everything, what we have seen is a process. The most important thing is the kind of approximation we have chosen for you. That matters a lot. Okay. Another thing here is, for the same problem we can see what happens if this is not at the center. You take this at an arbitrary location, both elements are not equal, and solve the problem. Identify what happens. Right? Next thing, something for you to think before the next class. Same problem, this time, this load P is acting here, this is some fraction. That fraction you choose. And the load P is acting here. Solve this using 1 element model and 2 element model. I want this total thing as only 1 element. Already we discussed how to tackle this. It is left to you how to explore. How to introduce the load vector when the load is not acting at the end point. It is somewhere in the middle, but still we need to use that as 1 element only. Any idea? What is the load vector due to point load? RPE. Look at the expression in your previous class notes. RPE. Huh? MPI transpose. FP. What is MPI? M at this location. If I call this point P, this becomes N1 at P, N2 at P, transpose, and FP. FP is only 1 dimension, only P. If it is at the midpoint, that will be P by 2 and P by 2. So here, just to verify by putting this equation, let us say if this is at L by 3. Any idea? If it is L by 3. What is the value of N1 here? N1 is equal to 2 by 3 here, and N2 is 1 by 3. So this here, this we are going to represent as 2/3 P here and 1/3 P here, and try to get the stress and strain the element for this and compare this with the actual values. Then you take this with 2 elements. What do you mean by 2 elements? This is one element and this one element. Where do you get the load P? In the middle. And you try this. Once you do this, then only you will try to understand what happens in these cases. A point load somewhere in the middle of the element. What is the analytical solution? What solution you are going to get by using one element model? What solution you get by choosing 2 elements? Okay? Then the next one, open any book, you have problems. Take the problems with 2 steps, 3 steps, 4 steps, and so on. Now you can take a problem from any of the books and see when there is a stepped bar, how to tackle. That you can practice from the book, whatever you have. Okay? So, if you have any doubt, we can spend some more time. Otherwise, we will close it today. Any doubts? Any questions? Okay.